Good morning. I hope everyone is having a wonderful day so far. My name is Celine Fawaz, and I am the Materials Engineering Team Lead in Albertaloop at the University of Alberta. In this presentation, I will be talking about the Aeroshell, specifically about its design, purpose, material selection, and manufacturing process. I would first like to start off with a statement that best describes our Aeroshell. The Aeroshell is a multi-piece vacuum-bagged carbon fiber encompassment. The design is a streamlined half body, serving as the most suitable aerodynamically efficient shape with an estimated drag coefficient of 0.09 to 0.15, as can be seen in Figure 1. The shape may be refined through computational fluid dynamics and finite element analysis simulations. The Aeroshell's purpose is to protect the pod against wind, debris, aerodynamic forces, and harsh environmental conditions. The reason to why we picked carbon fiber as the material of the Aeroshell is because of its unique properties. Carbon fiber is known to have a high strength to weight ratio. According to Zoltec, carbon fiber can be up to 5 times stronger than steel and twice as stiff, while bearing the same modulus of elasticity of 200 gigapascals. Carbon fiber also has good vibration damping, high fatigue, wear, and corrosion resistance. But corrosion resistance or corrosion still persists as an underlying issue when other metals are involved. We selected a 2x2 twill weave pattern as the most suitable pattern as it can conform to complex contours, has good pliability, and few stress concentrations. It also has great functionality, moderate stability, and formability. Another pattern is the plain 1x1 weave, which has a higher level of stability, but is not as pliable nor as well suited for layups with complex contours. It also has a lot more crimps that create stress concentrations and weaken the weave over time. The third pattern I would like to highlight is the unidirectional pattern, which is oriented in one direction, so you can tailor the layup however you'd like. However, it tends to fall apart and hence has poor workability, and it usually needs a bottom and top layer of woven carbon fiber when doing layups. Knowing the material that we were working with, the team decided to experiment with molds, infusion, and layups. By SolidWorks, 3 different 3D pattern molds were designed: the flat plane, the femoral hemisphere, and the arc. Each set was subjected to one of 3 curing conditions and to determine the most optimum curing setting. The decision was based on rigidity and curing time. The molds were optimized to eliminate any sharp edges, to avoid air pockets from the layups, to reduce stress concentrations, and to allow for easy removal from the molds. For all conditions, a generous amount of wax release agent was brushed onto the molds. 3 layers of carbon fiber were applied per mold, and the molds were allowed to cure for 5 days. For the preheating set, 20 milliliter of epoxy resin and 20 milliliter of hardener were separately heated in a 40 degrees Celsius water bath and then mixed. The heated mixture was thinly applied to the molds and between the carbon fiber layers, and the composite was left to cure for 5 days at 20 degrees Celsius. For the regular set, there was no preheating of the epoxy resin and the hardener. For the post-heated set, the carbon fiber parts were continuously heated over their curing time of 5 days. So this was the product of our experiment. The leftmost side, you have the regularly cured. The middle set is the preheated, and the rightmost set is the post-heated. What we notice is that adding thick coats of epoxy resin and hardener will result in a more flexible part. The resin carbon fiber needs at least 5 days to fully cure, and it is best to avoid humid or enclosed environments to avoid prolonged curing time and the result of a less rigid product. The best curing condition out of these 3 variations was achieved by the preheating of the epoxy resin and hardener. as all parts exhibited higher rigidity and an easier removal from the mold. The female hemisphere, relative to all other designs, was the hardest to remove, indicating a potential challenge posed by the aeroshell shape. There are 3 tests that we're hoping to get into. The initial vacuum bagging fiberglass mold testing, which we are doing to understand how vacuum bagging works, the properties of fiberglass and gel coat, the properties of the finished part, and to reduce supply, demand, and cost, and the use of low flashpoint chemicals. So there will be 9 foam molds with 3 layers of wetted polyester resin fiberglass and 3 layers of epoxy resin bound carbon fiber layers. The composites will be vacuum bagged. 1 set of 3 molds will be brushed with gel coat, another set will be covered with packaging tape, and the 3rd set will be covered with a release film. The second test will be mold infusion, where 3 fiberglass molds will be prepared based on the results of the previous test. The epoxy resin and the hardener will be drawn through by spiral tubing and point sources, spread along the length of the part by vacuum bagging. This will refine our understanding of the infusion vacuum bagging process. The 3rd test will be the manufacturing of the small-scale aeroshell, which is 1/3 of the scale, where the plug will be made out of foam covered with fiberglass, and the distribution of the resin hardener mixture throughout the mold will be through infusion. From the results of the previous tests, the manufacturing of the large-scale aeroshell will be optimized accordingly. And lastly, the testing of the aeroshell will include mounting onto the pod and wind tunnel tests, where we hope to ensure proper laminar flow and avoid as much as possible the formation of vortices. And the design will be optimized accordingly too. So this is the end of my presentation. Thank you, and I am open to any questions. Great.
Thanks. Nice work. Any questions from anybody? So what are you guys thinking is going to be the actual outside design of the, do you have like a render of how the aeroshell is going to look when you actually make it?
Yeah, we have a very rough idea, but again, we're still on to the optimization process, but we're trying to get the experiments of the carbon fiber done, and the design will come with time. But we have like an idea that it's going to look like a streamlined half body, not exactly, which is why there was a range of coefficients there, because it's not going to be exactly as that figure 1 that you saw.
Cool. Pujitha, did you want to ask a question? Can you explain the 3rd slide again?
Yeah, sure.
That's what you're asking.
Okay, I'll just reshare my screen here. Okay, this slide. So, wait, just to make sure, is it this one that you're talking about, or do you mean this one?
So the comment just said, can you explain once again in the 3rd slide? So I don't know if, Pujitha, if you have a specific question about the slide, or you just want the whole slide explained?
The
EF on layup.
Layup. So the procedure, this one.
I think so, yes.
Okay, awesome. Yeah, no worries. So basically what happened is that we did 3 molds. We designed them by SolidWorks, and we optimized them so that we remove any form of stress concentrations and to avoid any future issues. And we subjected them to one of 3 curing conditions. And the reason why we did that is because we're trying to understand what would give us the most rigid product and what would take the less curing time. So if we preheat it, which is basically like we heat the hardener and the epoxy at 40 degrees Celsius separately, and then we mix them together, and we applied very thinly to the mold and between the carbon fiber layers, which are 3 layers, and we leave that composite to cure for 5 days at 20 degrees Celsius. Whereas the regular is just the epoxy resin and the hardener mix, and you automatically apply them and you leave it to cure for the same amount of time. And the post-heating is just, you continuously heat the finished product. So after you apply the epoxy resin hardener, you continuously heat it over for 5 days over its curing time. So that's the difference between the 3 curing settings. And what we found out is that the preheating one is the best. So it's best for you to preheat your epoxy resin hardeners separately and then mix them instead of just mixing them regularly or continuously heating the carbon fiber resin mix. Yeah, you're welcome.